Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Glad to have you all back with us.
Hey everyone, excited for another dive into the deep end today.
Yeah, ready to get my mind twisted again, hopefully in a productive way. Hi, listeners.
Hello, everyone. Looking forward to a stimulating discussion as always.
So, I was reading this fascinating paper about the potential of combining neuroscience-inspired models with AI. It's really pushing the boundaries on how we might achieve more human-like intelligence in machines. I mean, think about it. We've got decades of research into the human brain, and we're barely scratching the surface in AI. Why not bridge the two more intentionally?
Yeah, I see where you're coming from, but I think we're already making huge strides with pure deep learning. We're seeing these massive models that are showing emergent capabilities that we didn't even think were possible a few years ago. It's less about mimicking the brain exactly, and more about finding the right algorithms and giving them enough data.
Emergent capabilities, but are they really intelligent? I mean, these models are fantastic at pattern recognition, but they don't understand the world in the same way we do. They lack common sense, the kind of reasoning we take for granted. They're still just glorified function approximators, aren't they? I think we need a new paradigm, something beyond just stacking more layers and feeding more data, something more neuro-symbolic.
I'm with you there on the shortcomings of pure deep learning, actually. It feels like we're brute forcing our way to something resembling intelligence when there's probably a far more elegant solution. I suspect it has a lot to do with how we represent and process information over time, and in relation to space. Deep learning doesn't really handle spatiotemporal data well, not in the way the brain does. I mean, we see an object move across a room. We can imagine its trajectory, what it looks like from different angles. Deep learning seems to just see it as a different set of pixels. We need to figure out how the brain is doing that, not how it recognizes cat faces. That's a tiny step in the journey, like the first step in crossing a massive canyon with no map.
Okay, let's unpack this. So, person two, you're saying the current deep learning approach is sufficient with more data and better optimization. What's the cutting edge? What are some specific examples you're excited about?
Well, look at the latest large language models, right? They can generate coherent text, translate languages, even write code with minimal guidance. We're seeing impressive zero-shot learning capabilities, and it's only getting better. These models are trained on massive data sets, and their scale is driving this emergence. The more data, the better the neural network's ability to recognize patterns and, essentially, form a rudimentary understanding of concepts in some capacity. For instance, the ability to form abstract concepts from raw input is very promising. This really shows how these networks can be more flexible than just function approximators. We're even seeing neural networks that are getting closer to reasoning. They might not be reasoning like we are, but they are going beyond simple memorization. For example, a lot of the new research coming out of Google DeepMind is pushing the boundaries of what neural networks can achieve with their attention mechanisms. For example, allowing them to focus on the most important aspects of the data. There are other architectures that are allowing the models to perform complex logical operations, such as chaining of arguments.
But isn't that reasoning a very shallow kind of reasoning? These models might spit out a logically consistent response, but they don't understand why that response is correct. They're manipulating symbols based on learned statistical associations, not on actual causal relationships or real-world knowledge. That's why they make these incredibly silly mistakes, like the ones you see in all the LM fails on the internet, where they answer the question literally, for example, asking it to count backwards from 10 and it responds 10, 9, 8, 7, 6, 5, 4, 3, 2 on 0 minus 1. Or if you ask it which is heavier, a ton of feathers or a ton of bricks, it often gets the answer wrong. That's because the understanding of weight is learned statistically, not logically. I mean, yes, they are doing impressive feats now, but they lack the capacity for true comprehension. I feel that these logical operations are just statistical correlations disguised as logical inference. There are examples where they fail to understand very simple logical statements.
Exactly. It's like they're really good at mimicking intelligence without possessing any. They're trained to statistically predict the next word based on what they've seen, but the understanding of that word is missing. They don't build a rich, dynamic model of the world that allows them to adapt to new situations with actual conceptual understanding. They cannot extrapolate beyond their training data in a meaningful way. I'm thinking, for instance, if you showed a deep learning model a single image of a horse and then showed it a single image of a zebra, it wouldn't be able to abstract the concept of, oh, they are both four-legged creatures. They are both related to one another in some manner. They're both an animal. It would just see two sets of pixels with no context or relationship between them. That is where I think the real breakthroughs will come from. It's like trying to build a house by stacking individual bricks without any understanding of structural integrity. That is what I think deep learning is doing, stacking bricks.
Okay, So person 3 and person 4, you're both pushing back on deep learning's limitations. So, what would a neuro-symbolic approach look like? How do we combine that with AI? And person 4, I want to come back to your point about the spatiotemporal aspects, but let's get the neuro-symbolic approach clear first.
Right? So, neuro-symbolic AI is really about combining the strengths of neural networks with symbolic AI. Neural networks are great at low-level pattern recognition, but they lack explicit reasoning. Symbolic AI, on the other hand, is good at logic and reasoning, but it struggles with noisy real-world data. So, neuro-symbolic AI tries to create systems where the neural network takes the raw input, does its pattern recognition magic, but then feeds the output into a symbolic system that can reason, plan, and form more complex and abstract representations of the world. You can think of it as combining intuition with logic. For example, we could use a neural network to identify objects in an image, like chair, table, and person, but then pass those labels, not the raw pixels, to a symbolic reasoning engine that can understand the relationships between them and infer things like the person is sitting on the chair, or the table is in front of the chair. Or take the horse and zebra example. The neural network can be used to identify the shapes and color of the horse and zebra, but the neuro-symbolic system can map them to concepts like animals, or four-legged or horse-like and zebra-like categories. It allows us to build an understanding of the world, not just a set of correlations in the pixel space. We can then build relationships between the concepts and have an understanding of the real world. So instead of relying solely on statistical patterns, we're working with explicit knowledge and reasoning. And that's crucial for achieving true, general intelligence because it's about manipulating concepts, not just sensory data.
I see the theoretical appeal, but I'm still not convinced that this level of explicit symbolic reasoning is necessary. I think that these capabilities are already being developed and the LLMs are already showing some level of internal concept forming. The sheer scale and complexity of neural networks could be sufficient to approximate the reasoning that the symbolic systems are trying to simulate. I think by combining the explicit reasoning with the neural networks, you are creating a bottleneck that will hinder the system, which is not needed. And practically speaking, building these symbolic systems is incredibly complex. We have to encode all the world's knowledge and relationships. Think of the CYC project. It's been ongoing for decades and hasn't shown a significant leap in the last decade. The current deep learning methods are much more flexible, scalable, and adaptable to new information. Isn't it just much more efficient to let the neural networks themselves learn these relationships through experience?
But that experience is still ultimately limited to its training data. I think you are underestimating the difficulty of inferring logical structures just from sensory data without any kind of explicit symbolic representation. It's about combining the power of subsymbolic processing and pattern recognition with explicit knowledge and reasoning. It's a kind of hybrid approach. I don't think one is sufficient on its own. The neural network gives us the raw data and extracts the concepts. The symbolic system gives us the framework for logic and understanding. The neural network is the intuition. The symbolic system is the rational mind. I don't think we can develop strong AI without both, at least not in a robust and generalized way. Look at a child. A child does not just experience the world, it formulates ideas, it builds on concepts, it uses language. Pure deep learning cannot do this. It can only predict the next word, not understand the concepts behind the words.
And I think the spatiotemporal element really connects with all of this. I mean, if you look at the human brain, there's a constant processing of information not just over time, but also across different spatial scales. We have hierarchical processing, from sensory inputs to abstract concepts, and it's all integrated in a way that deep learning just doesn't mimic. We can also imagine a rotating object in our mind or trace a route in our head. This is not being handled well by current AI. I mean, think of the hippocampus. It's a huge part of spatial navigation and memory. We need a way to represent information in a way that makes these kinds of operations possible. I think we need models that can translate between different coordinate representations, from the raw visual input to an internal representation that captures relationships and spatial dynamics, not just a vector representation. It is like if you were trying to build a house and the blueprints were in a completely different scale to the actual building. The builder would have to perform translations between these different formats to build the house. Deep learning does not understand the transformation between different forms of representations. It does not perform these translations, and so it is lacking the understanding. It's not just about what the objects are, it's about where they are, how they move, how they relate to one another in space and time. Deep learning just seems to use vector representations of what the objects are, and that is a poor representation for understanding the spatiotemporal dynamics that exist in the real world.
This is all really insightful. So, person 4, you're suggesting that we need a way to represent information in a more spatiotemporally grounded way. And person 3, you're saying we need to integrate symbolic systems for higher level reasoning. While person 2 is saying that deep learning can eventually approximate all this. Okay, let's say person 4, you're right about the spatiotemporal component. How would that change our approach to building AI?
I think we need to move beyond these static vector-based representations that deep learning typically uses. We need to model space and time explicitly. Think of the visual cortex. The brain doesn't just record pixels. It is constantly transforming visual input through different layers of abstraction, identifying features, then edges, then shapes, then objects. Each layer is performing a translation to a different coordinate system that represents the world. Think of the way the visual cortex detects edges. It is like a differential operator. It is calculating the change of light over space. These are like spatiotemporal calculations, and we do this in a continuous manner in the real world, not just on static images. We need AI architectures that can do similar transformations. Imagine a model that is able to learn the transformations between these representations, between different coordinate systems. I think that is the core of intelligence. The ability to map between different representations that are useful for different tasks. Think of how you can perceive an object from different angles. You can understand its 3D structure. It's not just a bunch of 2D images. It's an internal representation of the object. If we can develop the algorithms that can perform these transformations of representations, we can begin to build AI that is robust to all sorts of different viewing conditions and real-world scenarios. We can build algorithms that can anticipate what the world will look like in the future. We can build robust AI.
Okay, I can see the merit in that. But aren't we already implicitly capturing some aspects of spatiotemporal dynamics in models like recurrent neural networks, RNNs, and transformers? The attention mechanisms in transformers, for instance, do allow the model to weigh information based on its context, which is essentially time-based. And there is work on neural radiance fields that are able to model a scene in 3 dimensions. These are huge strides in the right direction and are showing how neural networks are able to model space to some extent. It's not a perfect representation, but it shows that the neural network can learn to model the scene based on the training data, with more data and better architectures. I think these models will continue to improve in their ability to capture these spatiotemporal representations. I think you are underestimating the power of these neural networks to approximate these complex operations. We might be closer to AGI with deep learning than you think.
But those mechanisms are still ultimately operating on a relatively shallow level. They're not building an explicit model of space and time. They're using statistical correlations between different parts of the input sequence to predict the next part. They're not actively reasoning about the spatial relationships between objects or inferring their trajectories in a way that is consistent with the laws of physics. It's like if a cat jumps behind the sofa, you can infer it's still there even though it's no longer in view. A neural network cannot do that without any additional knowledge being given to it in training. It does not have an understanding of occlusion or the laws of physics. It is a statistical correlation of the input data. That is all it is. I think the symbolic system can provide this framework for the understanding. It can provide a framework for understanding the rules of the physical world and so can guide the neural network to perform the right operations.
So it's like the neural network provides the data, the symbolic system provides the rules for interpretation, and the spatiotemporal representation provides the framework for reasoning about the world in a dynamic way, right? This all sounds like we are getting a clearer picture of a possible path to artificial general intelligence. It's fascinating how interconnected these ideas are.
Exactly, and we can start to build these systems with existing technology. We can develop algorithms that are able to perform these translations of coordinate systems. We can look at the algorithms that the brain uses for inspiration. For example, the visual cortex is constantly transforming the input from the retina into higher-level representations that allow the identification of objects and their interaction with the world. We can look into the algorithms for path planning in the hippocampus. We can also look into the algorithms for the cerebellum, which are used to control fine motor skills. It is not just about the connections, but the kind of transformations these connections are doing that are important. It's the algorithms that really are the core of the intelligence.
But I still think that this neuro-symbolic approach combined with spatiotemporal modeling is too much effort. I think that the power of deep learning with enough data will approximate this internal representation. With a more comprehensive data set and larger models with algorithms that take into account the spatiotemporal, I think that will be enough. We are already seeing hints of it with the latest large language models. We are close to AGI, maybe not in the way you think it is going to happen, but I think we are close.
But you're still implicitly assuming that these complex capabilities will emerge from brute force alone. I don't think that's a given. It's like trying to build a car by throwing enough parts in the air. It is possible, but very unlikely. I think a more guided approach, using neuroscience and symbolic methods, it has a higher chance of succeeding. We are essentially engineering intelligence, so we should take the approach of the engineers and not a random throw everything at the wall approach. It's more efficient and robust.
Okay, so let's take a step back and consider some concrete examples of this. We've talked about a few hypothetical ones, but let's see if we can connect this to some real-world applications. How might a neuro-symbolic system with this spatiotemporal understanding be used in a practical context? Maybe person 4. You can give us some practical real-world examples.
Sure. Think about autonomous driving, for example. Current self-driving cars rely heavily on deep learning for perception, but they still struggle with unexpected situations and generalizing to new environments. A neuro-symbolic system that incorporates spatiotemporal reasoning could do so much better. It could build a real-time map of the environment with all its complexities, not just a set of identified objects. This map would be used to predict the behavior of other cars, cyclists, and pedestrians, as well as anticipate how the road conditions might change over time. It could reason about the intention of other agents, not just their current position or trajectory. It would be a step change from just recognizing patterns. We could develop an algorithm that explicitly models the rules of traffic and predict based on an understanding of the real world, rather than just making statistical associations based on previous training data. Or think of robots in warehouses and factories. They need to navigate complex environments, pick up objects of different shapes and sizes, and adapt to changing demands. We need a robot that is able to understand the interactions that exist between objects in the real world. It cannot just see the objects, but understand its properties and what it is able to do with it. Or in medical diagnosis, think about analyzing medical images like MRI scans or X-rays. A neurosymbolic system with a strong spatiotemporal model could not only identify anomalies, but also reason about their potential causes and their relationship to other structures in the body. It could generate hypotheses about diseases. In summary, we need AI that can manipulate concepts and form real understanding of the world.
Those are all very compelling use cases, but I think deep learning will get us there eventually, just with more robust data sets and better training paradigms. I mean, we're seeing self-driving cars that are already pretty impressive. They're not perfect, but they're constantly improving. The latest models from Tesla are getting incredibly good at navigating most situations. I'm confident that these issues will be overcome with more time and data. And medical diagnosis algorithms are already outperforming doctors in some specific tasks. I think that current research paths are much faster in terms of development time and ease of implementation. It takes less time to train a neural network than to design and engineer a complex symbolic system.
But are those systems truly understanding what they're doing? Or are they just very good at pattern recognition? Are they truly safe to use in these environments? I think that we need to get beyond pattern recognition to reasoning. And it is the reasoning that will lead us to safer, more robust AI. Self-driving cars will still make mistakes, and we don't know when those mistakes will happen. And in medicine, the last thing you need is for AI to diagnose a disease with a statistically confident answer when it may be wrong. The system must be able to understand what is going on with the human patient and what the potential causes are. We need AI that can justify its conclusions, not just provide the answer. We need a system that is able to explain itself in a way that humans understand. A neuro-symbolic system is more likely to be able to do that because it deals with explicit concepts. A pure neural network-based AI is like a black box that we do not fully understand.
This is such a critical point, the explainability of AI. I think that's a huge area where the neuro-symbolic approach could have a massive advantage. If we could build systems that reason using explicit symbols, we could potentially trace back their logic and understand why they came to a particular decision. We can look at the internal representation of the AI and look at the concepts that it is manipulating. It would be a step forward from the opaque nature of most deep learning models. That would be a huge win for trust and safety. So, let's talk about the research that is happening now. What is the state of the art?
Well, there's a lot of research going into building more interpretable neural networks, for instance. We're seeing techniques that can highlight which parts of the input are most important to the model's decision. There is a lot of research into attention mechanisms. This can allow us to gain more insight into the internal working of the neural network. But I think that we should focus on making the deep learning models better rather than building complex symbolic systems. I think that the biggest issue that we are facing is the lack of data and better architectures. I think that as these improve, we will be getting closer and closer to AGI. There is still a huge gap to fill in terms of the quantity of data and the size of the models we're using, and we should continue to invest in that area. I think that that is where the biggest progress will be made, in terms of making deep learning models bigger, with more data and better training strategies. I think we will start seeing real AGI in the near future with the rapid pace of the field.
But these attempts to make deep learning more interpretable are still just scratching the surface. We're still trying to understand the internal logic of a black box by reverse engineering its behavior. I think that is a poor approach. The neuro-symbolic method gives you an explicit representation of the logic of the system. It is not hidden from you. You can see it and understand it. With this, you can be more confident that you are making a safe and robust system. And on the research front,
We're seeing more and more exciting work on integrating neural networks with knowledge graphs and logical reasoning systems. The work on graph neural networks is promising. It allows us to integrate symbolic information with neural networks. I think that we should continue to invest in research that is combining deep learning with the explicit reasoning power of neuro-symbolic systems. I think this is where the real breakthroughs will come from in the long term. We need hybrid systems.
And I think we're just starting to explore the potential of models that can learn the transformations between different coordinate representations. There are some labs experimenting with neural networks that are able to learn multiple frames of references. This, I think, is the core of intelligence. There is also the development of algorithms that are inspired by the visual cortex. I think that we should start taking inspiration from the brain, rather than just trying to build larger neural networks that are just mimicking pattern recognition. I'm very excited about where the research into these algorithms will go, as it can fundamentally transform how we think about AI. The algorithms are not just connections, but transformations of internal representations, and these are the core of the intelligence we are trying to develop.
It sounds like we're converging on a more nuanced understanding of the challenges and opportunities ahead. We're all agreed that there are limitations to the current AI approaches, but we have differing perspectives on the best path forward. The key takeaway for me is that there's not a single silver bullet solution, and there is great benefit in combining different research paths. Whether we focus on refining deep learning, incorporating symbolic reasoning, or building more spatiotemporally grounded models, the interplay between these different ideas is going to be critical. Maybe one of the paths is more correct, but we don't know that yet.
Yeah, I think that we can all agree that AI is going to change our lives. And in the end, we all have the same goal to build a robust and safe AI that will benefit humanity. Although we have different ideas on the best way to achieve it, we are all excited about the future and where the AI field is heading, whether it's deep learning, neuro-symbolic, or spatiotemporal modeling. I think the future is very bright and it will only get better.
I agree with that. It's a complex challenge and different approaches should be explored. And it's through these discussions that we can continue to clarify our thoughts and maybe see some common ground between our different views. I'm excited to see what comes next.
Yes, I think that the only way we can progress is by debating these different ideas and challenging our own assumptions. We are only at the beginning of this journey to building a generalized intelligence, and the best way forward is to take inspiration from the human brain. It's an amazing organ, and I believe that it holds the key to developing this technology. It will be interesting to see how the next few years progress. I think it's going to be very exciting.
Well, I think that's a great place to wrap things up for today. Thank you all for such a stimulating discussion. It's always a pleasure, and thank you everyone for listening. I think we covered a huge amount today. Join us next time for another exploration into the fascinating world of cognitive science.